Hi, we want to present about control of circulating drug levels in live animal. This is our group members. My name is Fatina Bila. Introduction. Traditional drug dosing methods have limitations and does not account for individual difference in genetics and physiology. We need a better way to administer drugs to patients that takes into consideration their unique characteristics. We propose a closed-loop system consisting of a biosensor, controller, infusion pump, and drug pharmacokinetics model. This system can provide real-time control of drug concentration, leading to more effective drug administration and better treatment outcomes. This is the block diagram of the system. We have PID controller, infusion pump, animal, and the real-time biosensor. The explanation. Our closed-loop infusion control system is an advanced technology that automates drug delivery by continuously monitoring drug levels in the bloodstream and adjusting the infusion rate accordingly. It consists of three main parts: a biosensor, a controller, and an infusion pump. The biosensor measures the drug concentration using spatial probes, while the controller uses a feedback algorithm to determine the ideal delivery rate. The infusion pump then adjusts the rate based on the controller's instruction.
Next, I will continue with mathematical model. There is three equations in mathematical model. For the first equation, is the quantitative resolution, which is QR, of the sensor was determined by calculating the ratio between the measurement intensity and assess analytical sensitivity. The analytical sensitivity represents the slope of the sensor's response function within the linear range of 0.1 to 1 micro. For the second question, is the case of the rabbits, the animal mass in grams is multiplied by the factor K equal to 9.9, while for rats, the factor used is K equal to 9.46. This calculation is performed to determine the appropriate dosage of CDDP. The desired total dose of CDDP is 4 mg per kilogram of the animal's body weight, and it is administered as a single bolus injection at a concentration of 1 mg per milliliter. This injection is given 2 to 4 hours prior to the infusion of dogs. For the last equation, to enable real-time measurement, dose calculation, and form control, we develop a customized analysis and control program using MATLAB. This program serves three main functions. Firstly, it retrieves and converts raw electrochemical data from the function set into calibrated concentration measurement. Secondly, it calculates the required infusion rate based on this measurement and the user input concentration set point. This is done using this discrete implementation of the parallel PI control algorithm, and the program communicates with the infusion pump to adjust the drug infusion rate accordingly.
Hello, my name is Marina Binti Halim. I will present Simuli model. This is the Simuli model. First, controller, infusion pump, animal, and real-time biosensor. Real-time biosensor have three parts: electrochemical scan, drug aptamer binding, and blood transport delay. Next, the explanation of Simuli model. The feedback loop can be modeled in silico. This model comprises the controller with proportional, integral, and derivative gains Kp, Ki, and Kd, which is the infusion pump drug Pk with an effective dilution volume Vd. and exponential alpha and beta phase elimination rates, and the real-time biosensor. S denotes the complex Laplace variable in transfer function form. Simulations based on this model enable in silico controller simulation and tuning for control in vivo.
Hello, my name is Siti Nurul Ain binti Kunsal Nizam, and I am going to present about the parameters. Okay, for the first equation is ut equals to kp exponent t plus ki. The control algorithm employed in our system follows a standard parallel pi controller design. It calculates the control output dose at a given time based on the proportional gain parameter, the error between the measured concentration and the desired set point concentration, and the integral gain parameter. The controller algorithm was discretely implemented with a fixed sampling time of 5 seconds. For the second equation is Ct divided by C0 equals to W alpha exponent negative alpha t plus W beta exponent negative beta t. To model and simulate the feedback loop of the control system, we utilize Simulink, a software designed for dynamical system simulating. The simulation incorporated the animal pharmacokinetics, real-time biosensor, and pi controller, considering all relevant transport and signal processing delays within the system. The PK and dots in rabbits and rats was represented by a biphasic concentration decay model, characterized by decay constant alpha and beta, as well as weighting constant W alpha and W beta.
Next, for the results, you can see in figure 3, which is closed-loop feedback control of dogs in vivo. Our system is accurately maintained in vivo drug concentration, which is in blue dots, at the desired set point, which is orange line, with a response time of 5 to 10 minutes in live conscious New Zealand white rabbits. A variety of concentration profiles can be realized continuously as a function of time. Orange arrows indicate start time of control infusion, and each row of panels represents a single experiment in one animal. In Z, shows detail of initial rise in upper right panel. Gray dashed line highlight 0 micro dots.
Okay, this is the result of figure 4. We conducted a study where we control the level of drug called dogs in the blood of different animals. We want to keep the drug concentration within a specific range during the infusion. In panels A, B, and C, show the dog's concentration in 3 animals as they receive the same dose of the drug. The desired range of drug concentration is shown as a white band, and the blue arrows indicate the duration of infusion. In panel D and E, we focus on the dog's concentration during the infusion when our closed-loop system was in control. The orange dashed line represents the target concentration we want to achieve. The data in panel D and E are from the same rabbits as in panel A and B, respectively. The orange arrow indicates when the feedback control infusion started and stopped. The white dashed line highlights a concentration of 0 microM dogs. In panel F, we analyze the time spent within the target concentration range during the infusion. The letters above the bar indicate which panel show the corresponding infusion data. Next, as you can see the result of figure 5. Closed loop infusion during acute drug interaction. A-B dogs plasma concentration in a single rabbit during infusion with dogs alone A, and the dogs infusion when co-administered administered with CDPB. C. Time in the target range, white band in A and B during infusion. Co-administration with CDDP result in dog's plasma concentration that fall outside the target range. DE. Dog's plasma concentration in the separate rabbit during dogs only infusion D, and then closed loop infusion of dogs with co-administered CDDP-E. The concentration set point is indicated by the orange dashed line. F time in the target range wideband in D and E during infusion. Closed loop dogs infusion maintains the target concentration for the entire duration of infusion, even in the presence of CDDP. Arrows indicate start and end of traditional blue or feedback control orange dogs infusion, white dash line highlight 0 micro dogs. Letter above bars in C and F indicate the panels that show the corresponding infusion data.
In conclusion, controller-based medical therapy offers promising solutions to challenges in the medical field. By using control-based approach, we can reduce variation among patients and make medical treatments more reliable. This technology has the potential to improve accessibility and effectiveness of treatment for a broader range of patients. The future of drug dosing lies in controller-based approach, which can revolutionize medication administration and enhance patient outcome. As control systems continue to advance, we can expect significant progress in precision and automation in medical therapies. That's all from us. Thank you.